technical term, steampunk. Steampunk is a genre of literature, art, and film. Steampunk stories take place during the Victorian era, when the Industrial Revolution has been humming, London is full of smog and Sherlock Holmesian mysteries, railroads are cutting across the American West for the first time, and people wear waistcoats and petticoats. Against these backdrops are futuristic technologies, such as automata, time machines, flying ships, and submarines. You might have encountered this steampunk novel, The Time Machine by H.G. Wells. It was one of the earliest steampunk works. It was written during the 1800s, but steampunk is very much with us still. The Invention of Hugo Cabret was a New York Times bestseller in the early 2000s. Enola Holmes was one of the first films released on Netflix due to the pandemic. It follows Sherlock Holmes's little sister, Enola. The film was a hit. I loved it, and the sequel is coming out soon. The Nevers is a show on HBO about women who have supernatural gifts. So these works reach back to the past and ahead to the future. This fusion of old and new creates a wonderful sense of nostalgia and adventure and exploration. The fans dress up in steampunk costumes with top hats and goggles and gears and gather at steampunk conventions. But this supposed fantasy of steampunk is now becoming a reality in my field of research. So I'm a theoretical physicist. So I model the universe mathematically, and then I find features of the world that we don't expect. So specifically, I work at the intersection of three fields: quantum physics, information science, and energy science. I'll briefly preview this intersection, then explain it in more detail. Information science is the study of how efficiently we can process information. Quantum physics is the study of the very small, such as single atoms and ions. They behave in counterintuitive ways that everyday objects can't. Scientists and engineers are now leveraging these counterintuitive behaviors to build quantum computers, which will process information in ways impossible for familiar technologies, such as the laptop I'm using to Zoom from. The thermodynamics is the study of energy. It was developed during the Victorian era to describe one of the cutting-edge technologies of the day, the steam engine. Today's cutting-edge technology include quantum devices, which are very, very different. So we need to re-envision the thermodynamics of the 1800s for the 21st century. And we need to ask how quantum engines would look and how they could operate. We need to reach back to the past and head to the future. The resulting fusion of old and new, I call quantum steampunk. So a genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. Let's look at each of those more closely. Information science is the study of how efficiently we can perform information processing tasks. These include solving computational problems, such as calculating a satellite's trajectory, communicating information, such as via the web, securing information cryptographically, and storing information in memories. We live in the information age, but what really is information? It's basically the ability to distinguish between alternatives. Say that a friend of yours asks whether the pub down the street, in Victorian London, of course, is open or closed. You peer through the window and see either foaming mugs or cleaned mugs sitting upside down on the counter. You've gained the ability to distinguish whether the pub is open or closed. You've gained information. We measure quantities in units, such as seconds or teaspoons. What is the basic unit of information? It's called the bit. It's the amount of information you gain if you have no idea of the answer to a yes or no question, and you learn the answer. Say that when your friend asks about the pub has a probability one half of being open and one half of being closed. When you peer through the window, you gain one bit of information. We can encode a bit in a physical system that can be in one of two possible states. In a familiar computer, a bit is encoded in a transistor that has the value 1 or the value 0. Quantum physics is the study of very small things such as single electrons or atoms or particles of light, which we call photons. These systems behave in ways impossible for everyday systems such as books and microphones and human beings. Everyday systems are large, are massive, and have many, many particles. We call them classical. Quantum physics is non-classical. What are these counterintuitive quantum behaviors? We can come to understand one of them to an extent by imagining that some young physicist, let's call her Audrey, has an electron and her brother Baxter has another electron. The two siblings can bring the electrons together and perform some operation on them that creates entanglement between them, depicted in cartoon fashion here. Entanglement is a relationship that quantum particles can share and classical particles cannot. Here's one glimpse of how it works. Suppose that Audrey measures her particle and the measurement has one of two possible outcomes, which we'll label 1 and 0. For instance, Audrey can measure whether her electron has a lot of energy or a little energy. If the two particles are entangled as strongly as possible, Audrey cannot have any idea of which outcome she'll obtain. So the 1 outcome and the 0 outcome have 50-50 chances. Now, suppose that instead, Audrey measures her particle and Baxter measures his. The siblings can now predict something about the joint outcome. For instance, if Audrey obtains a 1 in an example, she'll know that Baxter will obtain a 0. And if she obtains the 0, she'll know that Baxter will obtain the 1. Furthermore, there is a measurement that the siblings can perform jointly on a pair of particles together, such that the siblings can predict with exact certainty the outcome in advance. So there's some information that isn't in Audrey's particle, it isn't in Baxter's particle, and it isn't in the sum of the two particles addressed independently. It's sort of spread across the pair. So when it comes to entanglements, the whole is greater than the sum of its parts. Scientists and engineers are now leveraging entanglements in quantum information science. The quantum information science is the study of how we can use quantum phenomena to process information in ways forbidden for classical systems. So quantum computers, which we are building now, will be able to solve in minutes certain computational problems that would take even supercomputers many, many years. An important application will be research and development in material science and technology. That might sound a bit dull, but in some countries, food security is at crisis levels. So fertilizer is extremely important. We invest about 3% of the world's entire energy outputs in fertilizer production. Why do we spend so much energy? Because we produce fertilizer using an old technique from 1909. Bacteria can accomplish the same goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. The molecule, though, is quantum. So a quantum computer will naturally be better suited to cracking the molecule's secrets, and if all goes as hoped, which is a big if, then transforming fertilizer production and much of energy use. A little wonder that governments across the world are pouring funds into quantum research, technologies, and education. In 2018, Congress passed the National Quantum Initiative Act, which provided $1.2 billion for quantum efforts. Even more astoundingly, the Senate passed the act unanimously. So everyone on the Senate actually agreed about it. Like governments, companies are investing in quantum science. Microsoft, Google, IBM, Amazon, Honeywell, and loads of quantum startups have quantum teams. Now, this object belongs to IBM. This is not a quantum computer, even though it looks cool enough to be one, doesn't it? This object, which actually many people think looks steampunk, holds a quantum computer which fits on a small chip. This chip needs to be at low temperatures in order to support quantum phenomena such as entanglement. So this device cools the quantum computer to temperatures below the temperature of outer space. Cooling leads us to the third element in our triumvirates, thermodynamics. Thermodynamics is the study of energy, the forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in two forms, heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized and so not directly useful. Work is coordinated energy that can be directly harnessed to power a factory or raise an anchor. Heat engines convert random heats into coordinated work. Heat engines drove the Industrial Revolution by powering the first factories. People started wanting to know how efficiently engines could operate. So they developed the theory of thermodynamics, giving it a practical bent. But the practical questions led to fundamental questions like, why does time flow in only one direction? And do materials really consist of particles too small for us to see? Now, cooling, expelling heat, is a thermodynamic process. But how do you measure the heat that's emitted by a quantum system that's cooling down? You could measure the heat emitted by a classical system by measuring the system's heat, cooling the system, and measuring the heat again. The initial energy minus the final energy will be the heat lost. But quantum systems are more delicate than classical systems. You might have heard of Heisenberg's uncertainty principle. Werner Heisenberg was a German physicist who helped found quantum theory during the 1920s. He intuited that if you measure a quantum system, you disturb it. If you measure a quantum system's energy, you actually change the energy. So how we can measure quantum heat or even conceive of quantum heat isn't straightforward. Furthermore, this fridge here is a large classical system. Could we build a fridge from a quantum system? How small could we make it? More broadly, just as there are information processing tasks, there are thermodynamic tasks, such as refrigerating and powering factories and charging batteries. Given that quantum phenomena such as entanglement can benefit information processing tasks, can they benefit thermodynamic tasks? How can we more generally extend this Victorian theory of thermodynamics from large classical systems such as steam engines to small quantum and information processing systems? These questions underlie quantum thermodynamics, my field of research. This field shares its aesthetic, its spirit with steampunk, which is why I call my work quantum steampunk. Quantum thermodynamics stretches back to the 1930s. During the 1950s, researchers designed the first quantum engine. It consists of one atom that you can use in a maser, which is like a laser, but whereas a laser emits visible light, a maser emits microwave radiation. It turns out an engine doesn't need gears and cogs and other moving pieces. It needs only one atom. Over the past decade, quantum thermodynamics has experienced a boom. Here's a photo from my community's big annual conference in 2018. We met in Santa Barbara, that's why the scenery is gorgeous. Why has quantum thermodynamics been booming? Because quantum information science matured during the early 2000s. It now offers a mathematical and conceptual toolkit for understanding quantum systems through how they store and process information. Quantum information science also offers exquisite experimental opportunities. Labs have achieved extraordinary control over tens to hundreds of thousands of atoms, ions, and photons. We've been using all of these tools of quantum information to build and test a theory of quantum thermodynamics. Here's an example. We'll start with a classical story that showcases the interplay between information and energy. Then we'll see what quantum physics adds. We can store a bit of information not only in a transistor, but also in a gas particle in a box. So this particle is going to be classical at first, like a miniature basketball. It's a really, really simple gas. If the gas is on the right-hand side of the box, we'll say it encodes a 1. If it's on the left-hand side of the box, it encodes a 0. By the way, this image is by Todd Cahill, the steampunk artist who illustrated my book. He had no experience whatsoever with quantum physics, but he managed to make gorgeous illustrations. Suppose that we have no idea where in the box the particle is. The position is totally random. Suppose that we want to reset the particle's position to the box's right-hand side, to a nice clean state. This is like taking a messy sheet of scrap paper that's been scribbled on randomly and erasing it to a nice clean state. To erase the bit encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature, through the box's walls. To reset the position, we can slide a partition into the box near the left-hand wall, and then push the partition to the box's center. The gas will end up trapped in the right-hand side. At what cost? We compress the gas, but we expend energy, namely work. So resetting the particle's position or erasing our bit of information, an information processing task costs work, a thermodynamic resource. A priori, information and energy seem like they don't have to have anything at all to do with each other, but they turn out to be inextricably bound up. But what if we add quantum physics to this mix of energy and information? Suppose that we want to erase not a classical bit of information, but a quantum bit, a qubit, a basic unit of quantum information. We can encode a qubit in an electron, like the one that Audrey had a few minutes ago. So Audrey's qubit can be entangled with Baxter's qubits in some fixed temperature environment. Remember, if Audrey's particle is entangled with Baxter's particle as strongly as possible, and then she measures her particle, she has no idea whether she'll obtain a 1 or a 0. The outcome is totally random. So Audrey's qubit resembles the gas particle bit whose location, left or right, 1 or 0, is totally random and needs erasing or resetting. Well, Audrey can erase her qubits while actually gaining work that she can use to raise a battery or lift a tiny weight. Now, this result should surprise us because we just concluded that we have to spend work to erase information. The trick is to sort of burn the correlations between the qubits. Entanglement serves as a kind of thermodynamic fuel in the presence of heat. So quantum phenomena such as entanglement can serve as resources in thermodynamics, in gaining work, as well as in information processing, in erasing information. If we gaze into the future of quantum steampunk, what do we see? First, I think quantum thermodynamics will spread. Just as quantum information science has transformed other fields, such as thermodynamics, we're now using quantum thermodynamics as a toolkit to understand black holes and chemistry and materials anew. Second, quantum thermodynamics has its roots in theory. It's provided fundamental insights into, say, what separates quantum physics from classical physics, or what it really means for time to flow. But experiments are growing in quantum thermodynamics, testing the theory and sparking new theory. A third opportunity is to make quantum thermodynamics actually useful, not only fundamentally interesting, in the spirit of the Industrial Revolution. For instance, I'm working with experimentalists in Sweden on a quantum refrigerator for cooling quantum computers. Quantum thermodynamics is an incredibly exciting emerging field. It is vibrant and growing. It offers both fundamental insights and technological possibilities. We can read about steampunk in novels, but this genre of science fiction is coming to life at the intersection of quantum physics, information science, and thermodynamics. So the fantasy of steampunk is becoming a reality. Thank you.
Very nice. Thank you, Nicole. The first question I have for you is just a curiosity. You mentioned a quantum engine in the 50s. Who did that?
That was a group in the United States. I think they might have been, I think that a number of the authors were affiliated with Bell Labs. Bell Labs in physics has a kind of folklorish standing. It produced so many Nobel Prizes. It produced so many great innovations. It also produced some great innovations in information theory. So a number of the authors were based there. One of the there were two papers, one in 1959, and then an expanded one in 1967. One of those had lead author of Scoville and also Jusic, if I'm pronouncing the name correctly.
And what did they do with that? It was just a theoretical exercise, or they did something with it?
It was a theoretical exercise, but around that time, people were basically inventing and playing with for the first time lasers, the field of quantum optics in which lasers belong was undergoing a transformation. So people were thinking really hard about and also realizing in the lab the ideas that they brought into play.
And can you give us a 2-minute short history of quantum thermodynamics?
Sure. The people in the 1930s started thinking about quantum thermodynamics. So right after quantum theory was developed, it was formulated in the 1920s and 1930s, people started wondering if quantum phenomena such as uncertainty could explain thermodynamic phenomena such as the arrow of time. They, I think, didn't make a whole lot of progress then, but this first quantum engine was proposed in 1959. Then during the 1970s, I believe, there were a number of mathematical developments that were quite important. The people started modeling quantum systems, exchanging heat and information with their environments, and we use a lot of those mathematical tools still today. During the 1980s, there was some work that was quite theoretical and quite foundationally minded based in the United States. There was some at MIT, some inspired by Ed Janes, who was in the Midwest. They thought about the laws of thermodynamics. So they were thinking the laws of thermodynamics, such as the energy of the whole universe is conserved, and the second law of thermodynamics basically states time flows in one direction. These are the core of thermodynamics, and they were thinking, can we reformulate these laws, which started being codified during the 1800s before people knew anything about quantum theory, in a way that included quantum systems. But during this time, people, quantum thermodynamics was not popular. And some people even said quantum thermodynamics was an oxymoron because thermodynamics was invented to describe large systems like steam engines, so it couldn't possibly have anything to say about quantum systems. During the next few decades, there was very little work on quantum thermodynamics, although few people like Ilya Prigogine thought about it. But during the past decade, there's been this enormous boom, in part because now we have great theoretical and experimental tools from quantum information science. The boom has really been centered in Europe. There have also been hotspots in Israel, it's been a hotspot for a number of decades, and Brazil, Germany, and the United States is starting to catch on. There are a few of us doing quantum thermodynamics here and working really hard to expand it here.
And so changing topic, you mentioned quantum computers. We've been hearing about quantum computers for a while. Every 2 or 3 years, it sounds like they're coming, but what's the real status and why? I mean, why it's taking so long should be obvious. For those who know quantum mechanics, it's obviously not easy engineering. But so what's the real status, and where do you see it? What's the time frame, in your opinion?
As you alluded to, there's a joke that quantum computers are always 20 years away. People started really, well, the roots of quantum computing came about during the late 20th century when people proposed the idea of a quantum computer, including Richard Feynman, but a lot of interest really came together in 1994 when people started working really hard on building quantum computers. The amount of control achieved today is really fantastic. So there are 2 types of quantum computers, and they have different statuses. There are quantum simulators, and these are computers that can solve a small class of problems. Quantum simulators exist. They have up to about 1 million particles, and they're in labs across the world. They've been used to do quite interesting things, such as realize new phases of matter that have never been realized before. So those are in pretty good shape. But they are limited to solving just certain classes of problems. What people are even more interested in, perhaps, are universal quantum computers. These are quantum computers that you can program to solve any problem you can solve with a quantum computer, and then reprogram it to solve any other such problem. These quantum computers, we have small versions of them. They have tens of particles, maybe up to 100 particles or so. They're small and they're noisy. There are a few problems that these computers have arguably, or it's believed, managed to solve much, much more quickly than any classical computer. The most famous example is a Google experiment from 2018. So they solved a toy problem with their quantum computer in under 4 minutes, and they estimated that a classical computer would take something like 10,000 years to solve that problem. That number has been debated since, but this is still a significant success. What's going to be really important as the next stage is implementing error correction to get rid of these errors in these noisy quantum computers. That's going to require scaling up these quantum computers to much, much larger sizes and gaining even better control. That is going to take a while. Personally, I expect it'll take a couple more decades, but I really do believe that we will achieve universal quantum computers as long as funding doesn't dry up.
And you mentioned these quantum computers made of particles. What kind of particles?
It depends on the type of the quantum computer. There are many different platforms, different types of hardware from which people are building quantum computers. Some of them, there are a few main contenders. One is trapped ions. For instance, a group in Maryland does this really well. So these are ions that are trapped and controlled with laser beams. There are also superconducting circuits. These are small circuits in which current can flow forever by the strange properties of quantum mechanics without ever dissipating. And these are larger. They're actually printed on a chip, so you might be able to see them by eye, but as long as they're at really, really low temperatures, then they exhibit quantum behaviors. Also, ultra cold atoms are another option. Some people are using just photons, particles of light. So there are a lot of possibilities. And actually, I wouldn't be surprised if the quantum computers that we end up with and end up using a great deal will be hybrids of multiple platforms.
Very good, very informative, very well explained. So the book is out, Quantum Steampunk. I assume we get everything in this book.
Yes.
And a lot more than we discussed tonight.
Absolutely.
Great.